Okay, part D for Newton's third law of motion. Relevance of problem. The problem connects to Newton's third law because it uses collision between two objects, just like the pendulum experiments. Newton showed every action has an equal and opposite reaction, and this problem uses the same idea but with real numbers to show how it works in modern examples. The new numerical problem is a 0.55 kg pendulum ball collides with a 0.80 kg pendulum ball. During the collision, the first ball applies a force of 4.6 N on the second ball for 0.10 seconds. Question: what is the impulse delivered during the collision, and what is the change in the momentum for each ball? Okay, benefits of the problem. This problem helps you understand Newton's third law in real collisions. Using real numbers show how forces create equal and opposite reactions and how momentum changes during impact. It makes the law more practical instead of just something you memorize. Skills gained. Solving this problem teaches you how to calculate impulse and momentum, work with force and time, analyze collisions, and understand how two objects affect each other during impact. These are the same skills used in physics labs and engineering. What you can solve next. After learning this, you can move on to harder problems like finding rebound speeds, comparing elastic and inelastic collisions, predicting motion with multiple objects, and analyzing real-world impacts like car crashes or sports. Development of the problem. This problem was built from scratch using the same collision idea Newton used with pendulums, but with modern numbers. The masses, force, and time were chosen to make it a realistic physics situation where Newton's third law can actually be calculated, not just described. Not too simple. It isn't too simple because it uses real values for mass, force, and time. You have to calculate impulse and momentum change, which shows the full action-reaction relationship instead of just memorizing the law. Not too difficult. It's also not too difficult. It only uses one formula and a clear collision setup. The numbers are realistic and easy to work with, so anyone who understands Newton's third law can solve it without advanced math. Difficulties in creating the problem. Creating a new physics problem is hard because it has to be original but still match the topic, which is Newton's third law of motion. I had to avoid copying textbook examples, avoid making it too conceptual, and make sure the math wasn't too complicated. I also had to make sure it clearly showed action and reaction. Uniqueness of problem. Most problems about Newton's third law are simple and do not use real numbers. Mine is different because it uses realistic pendulum collision with specific masses, a measured force, and a collision time. It requires real calculations instead of guessing. How the problem is different. Typical problems only say forces are equal and opposite. My problem connects that idea to real values for mass, force, and time. The solver has to calculate momentum changes instead of identifying the forces. What was added to make it unique? I added realistic masses, a specific collision force, the exact impact time and required impulse, and momentum calculations for both objects. These details make the problem original and not a basic textbook example. How the problem goes above and beyond. This problem goes further by connecting Newton's third law to measurable quantities. It shows the cause, which is the force during collision, and the effect, which is the momentum change. It helps the solver understand how equal and opposite forces work in real physics. Visual for problem, force versus time. This graph shows how the force changes during the 0.10 second collision. The force rises when the balls first touch, reaches a peak during the strongest part of the collision, then drops as they separate. Significance of the points at the start, from 0.00 to 0.02 seconds, the force begins to rise as contact starts. In the middle of 0.04 to 0.06 seconds, the peak force of 4.6 newtons show the hardest part of the collision. At the end, from 0.08 to 0.10 seconds, the force goes down as the balls move apart. Relationship in the data, the graph forms a simple rise, peak, and fall pattern. This shape is common in real collisions and helps find impulse by calculating the area under the curve. Formula for the problem. For the main formulas, the first one is impulse equation. Impulse equals force times delta T. The next formula is for momentum. Delta P equals impulse. For Newton's third law, the force on ball 1 from ball 2 is equal and opposite to the force on ball 2 from ball 1. For the units, force is measured in newtons, time in seconds, mass in kilograms, velocity in meters per second, impulse in newton seconds, and momentum in kilogram meters per second. For the variables, F is the force during collision, delta T is the collision time, J is the impulse, delta P is the change in momentum, M1 and M2 are masses of the two balls, and V1 and V2 are the velocities when you need to relate motion to momentum. Solutions for problem. For this problem, the first ball has a mass of 0.55 kilograms. The second ball has a mass of 0.80 kilograms. The force during the collision is 4.6 newtons and the collision lasts 0.10 seconds. Step 1 is the impulse formula. Impulse equals force times delta T. Using the numbers 4.6 newtons times 0.10 seconds gives an impulse of 0.46 newton seconds. Step 2 relates impulse to momentum. Since delta P equals impulse, the change in momentum for the second ball is positive 0.46 kilogram meters per second. This means momentum increases in the direction of the force. Step 3 uses Newton's third law. The first ball receives an equal and opposite impulse, so its change in momentum is negative 0.46 kilogram meters per second, which means its momentum decreases in the opposite direction. Final answer, the impulse is 0.46 newton seconds. The second ball momentum change in positive 0.46 kilogram meters per second. The first ball's momentum change is negative 0.46 kilogram meters per second. These equal and opposite momentum changes match Newton's third law. Verification for the problem. To check the math, the impulse is force times delta T, 4.6 newtons times 0.10 seconds gives 0.46 newton seconds. That means each ball changes momentum by 0.46 kilogram meters per second in opposite directions, and repeating the calculation gives the same result. The value also makes sense. The force and time are small, so an impulse of 0.46 newton seconds is reasonable for a light pendulum collision. If either number were much larger, the impulse would also be larger, so the scale fits. The units check out too. Newton's time seconds equals Newton seconds. which is the same as kilogram meters per second. The unit for momentum. One ball has a positive change and the other has a negative change, and together they add to zero, which matches an isolated collision. This verification shows that the problem follows Newton's third law and conservation of momentum. The equal and opposite forces create equal and opposite momentum changes, making the problem consistent with both the theory and the experiments.
For this project, my brand new problem connects directly to Newton's third law because it uses equal and opposite force and real collision. Earlier in my project, I explained how Newton's works to understand motion and forces. My new problem takes those ideas and applies them to two carts that collide so we could calculate their final velocities. It relates to the topic because it shows how actions and reaction force affects real objects in motion, not just theory. Benefits of the problem is understanding my brand new numerical problem helps students see Newton's third law as more than just definitions. They learn how to action and reaction force work in real measurable situations by calculating forces, values, amplitude, and changes in velocities. Students will develop a deeper understanding of how equal and opposite force shape motions during collision, pushing, or pulling interaction. For my problem involves two carts on a frictional track. Cart A is 2 kilograms and cart B is 3 kilograms. A force of 12 newtons act for 0.4 seconds during the collision. Because of Newton's third law, each cart receives the same implosion but in opposite direction. The equation is to calculate the final velocity of each cart after the collision. Some skills gained is mathematical application, data interruption, critical thinking, and scientific reasoning. Other problems students could tackle after solving this is two-dimensional collision or angle forces, momentary conservation, problems in kart sports, multiple object systems, and real-life data using sensors. I developed this problem from scratch by starting with a realistic lab setup that students actually use. It's not too simple because it requires multiple answers. Because it's also not too difficult because the numbers are cleaned and the method follows a clear pattern. When creating the problem, I avoid making it unrealistic, too long, or just a plug-in equation. I made sure the difficulty level matches what we learned in physics. This problem is unique because most textbooks or internet examples only give one mass or ask about simple force pairs. Mine goes further by giving two masses a collision time and requiring full momentary check. I add realistic lab values, equals and opposite of forces, and actually experience step to make it different from basic worksheets. It goes above and beyond because it connects modern lab tools with classical physics. This graph shows how mass of each cart compares to itself in velocity. Cart A, which is lighter, has a bigger change in speed, and cart B has a smaller change. These data points show exactly how Newton's third law affects motion. The visual helps make the math easier to understand because we clearly see the relationship between mass and velocity. The main formula I used was the implementarity equation. Implosion equals mass times change in velocity. I also employed equal force times time. The variables include mass, velocity, force, time, and implosion. The units are newtons, seconds, kilograms, and meters per second. These are standard units for any collision problems in physics. To solve this problem, I first calculated the implosion. 12 newton times 0.4 seconds gives 4.8 newton seconds. Then I divided the implosion by each cart mass to find their change in velocity. Cart A ends up moving at negative 2.4 meters per second, and cart B moves up at positive 0.6 meters per second. Finally, I verified momentum was equal and opposite, which proves the answer is correct. I checked the solution by confirming the momentary change were equal and opposite, just like Newton's third law requires. I also compared the answers to a reasonable range of values, and they fit perfectly. The unit matches a direct, makes sense, and the numbers are realistic from a real-life experience. The solutions help support the whole project because it shows Newton's third law is used in an actual calculation, not just explained in words.
This problem demonstrates Newton's third law. For a reaction, there is an equal and opposite reaction. It connects directly to earlier parts of the project by applying the law to a real-world scenario involving motion and force. The situation involves two ice skaters pushing off of each other and moving in opposite directions. The problem requires calculating the acceleration of one skater based on the force exerted and the mass of both skaters. It emphasizes how forces always come in pairs and affect both objects involved. Problem statement. Two ice skaters push off of each other. Skater A has a mass of 60 kilograms and experiences an acceleration of 1.5 m divided by s squared. And what is the magnitude of the force skater A exerts on skater B? If skater B has a mass of 80 kilograms, what is their acceleration? Benefits of the problem. Solving this problem builds intuition about how forces act between objects. It reinforces the idea that motion is mutual. Both objects respond to the same force. Students gain skill in applying Newton's law to dynamic systems. This prepares learners for more advanced topics like momentum conservation and collision analysis. After mastering this, students can analyze rocket propulsion, vehicle collisions, and biomechanics. Development of the problem. The problem was inspired by real physics demonstration involving ice skaters or carts on low friction surfaces. It avoids being too simple by requiring two calculations, force and acceleration. It avoids being too difficult by using straightforward values and Newton's second law, F equals ma. The scenario is familiar and visual, making it easier to understand and explain. It avoids conceptual ambiguity by requiring actual numerical solving. Uniqueness of the problem. Unlike textbook problems that isolate one object, this problem shows the interaction between two. It includes both force and acceleration, emphasizing the reciprocal nature of Newton's third law. It uses a relatable context, ice skaters instead of abstract blocks or pulleys. It adds depth by showing how the same force affects different masses differently. It's original and not copied from any standard source. Here's a visual for the problem. The blue line at the top is skater A. It rises to 90 during the push-off, then falls back to 0. And the red line is skater B, mirrors skater A's line, showing negative 90, showing that it is equal and opposite. The time axis is 0 to 2 seconds, representing the duration of the push-off. This makes Newton's third law crystal clear. The forces are equal in magnitude but opposite in direction, and they act over the same time interval. The formula for the problem, Newton's second law, F equals ma, where F is the force, m is the mass, and a is the acceleration. Newton's third law, F1 equals negative F2, equal in magnitude, opposite in direction. The variables are m equals 60 kilograms, A1 equals 1.5, M2 is 80, and A2 is what we're looking for. The units, force is newtons, mass is kilogram, accelerations is meter per second squared. The solution for the problem. Calculate force exerted by skater A, which is F equals mxa, which is 60 kilograms times 1.5 meters squared equals 90. Step 2. Apply Newton's third law. Skater B experiences a force of 90 in the opposite direction. Step 3. Calculate skater B acceleration. A equals F divided by m equals 90 divided by 80 kilograms equals 1.125 meters per second squared. And final answer, skater B accelerates at 1.125 meters squared meters per second squared in the opposite direction. Verification: units are consistent. N equals kilograms times mass divided mass by meter squared. The force is equal for both skaters, confirming Newton's third law. The acceleration values are reasonable and match expectations based on mass. The solution shows how Newton's third law governs interactions in motion. It connects back to the project's theme by demonstrating reciprocal forces in a dynamic system.
Relevancy of the problem. This problem relates to Newton's third law because jet propulsion in Newton's third law is in action. The engine pushes exhaust gases backward, which is the action, and then those gases push the jet/rocket forward with an equal opposite force, which is the reaction, creating thrust. Early on, we further discussed how every push and pull generates a counter force. So the push and pull is what the jet does to the gases, and the counter force is what the gases do back to the jet, making it move. New numerical problem. A rocket engine injects exhaust gases backward at a speed of 500 meters per second with a mass flow rate of 10 kilograms per second. Question: what is the thrust force produced by the engine? Benefits of the problem. Understanding this problem helps connect Newton's third law to real life. It shows how every action has an equal and opposite reaction. It isn't just words in a book. It literally explains how rockets and jets move. Think about how exhaust gases push backward and the rocket moves forward makes the idea of counterforce easier to picture and remember. Skills gain. Using formulas like F equals m times v, which strengthens your ability to handle physics and calculations in other situations. Seeing how numbers relate to real things like how much force an engine creates. Other problems someone could tackle after solving this problem: find the recoil velocity of the cannon using conservation of momentum and Newton's third law. Using conservation of momentum in action and reaction to find both final speeds of two cars push off of each other, like students on skateboard pushing apart. Development of the problem. This problem was developed to turn the idea jets push back gas pushes jet forward into numbers you can calculate and check, which makes the physics much more concrete. I chose numbers that give a clean answer, 5,000 newtons, so you can see clearly how jet propulsion plus Newton's third law turn into a simple calculation. Not too simple. This problem is not too simple since it's not a random arithmetic. You're using the authentic thrust relation, which comes from conservation of momentum and Newton's third law. It forces you to unpack the physics idea. To solve it, you have to recognize that mass flow rate times exhaust speed change momentum per second. Changing momentum per second is force in newt. That ties together momentum, force, and action reaction. Not too difficult. This problem is actually very doable because you only need one main formula, F equals m times v, and it includes straightforward numbers to plug in. The equation only asks for one main thing, which is the thrust force, which can be calculated using the formula. Difficulties creating the problem. Some difficulties in creating the problem was choosing realistic numbers. You want exhaust speed and mass flow rate, which that could be real for a small rocket but still give a clean answer like 5,000 newt. Balancing realistic and clean math was kind of tricky. I also had to keep in mind that the problem had to hint in action, reaction, and momentum change to demonstrate Newton's third law. Uniqueness of the problem. This problem links to real jet physics. It doesn't just say a force acts on a block. It specifically uses mass flow rate and exhaust speed, the actual ingredients of a real jet/rocket thrust. This problem also shows Newton's third law with a number. Most Newton's third law examples are verbal. You push the wall, it pushes back. This problem turns that into a numerical reaction force, 5,000 newt, making the action-reaction idea measurable. How the problem is different. Many modern problems say a force acts on a box. Mine uses flow rate and exhaust speed, the actual quantities engineers use for jets and rockets. Most modern problems either have messy numbers or lots of steps or are basic with no real world meaning. What was added to make it unique? Some components I added are, instead of a force pushes a block, I made it about a rocket engine with an exhaust gas. That connects directly to modern jet propulsion, not just abstract motion. 10 kilograms per second and 500 meters per second give a neat answer, 5,000 newt, on purpose so the focus stays on understanding, not messy math. At the same time, those values still feel believable for a small thruster. How the problem goes beyond and above. This problem goes above and beyond because even though it only acts for thrust, it's really about exhaust gas gaining, backward momentum, rocket feeling an equal forward force. So you're practicing Newton's third law momentum. Visual for the problem. Thrust versus mass flow rate at fixed speed. This graph is visual proof that for a fixed exhaust speed 500 meters per second, thrust and mass flow rate have a linear relationship. Horizontal x equals mass flow rate, kilograms per second, how much thrust the engine throws out each second. Vertical axis y, thrust Newton, how hard the engine pushes the rocket. Because the points line up in a straight line through the origin, it shows when you increase mass flow rate, the thrust increase in direct proportion. If you double the mass flow rate, you double the thrust. Significance of the data points, case 1 through 5. Each time the mass flow rate doubles, 2, 4, 8, etc., the thrust doubles, 1,000, 2,000, 4,000 newtons. Case 5, 10 kilograms per second, 5,000 newtons. It's exactly your original problem. Relationship in the data, the graph of thrust versus mass flow rate is a straight line through the origin. That means that the relationship is linear. Mathematically, F equals 5,000 m, so thrust is directly proportional to mass flow rate. Formula for the problem, main formulas used, core thrust formula, thrust from flow, mass flow, and exhaust speed. This is the direct way to solve the problem. Momentum plus relationships, how the formula is born. Momentum of mass, P equals mv. Force as a rate of change of momentum. Combine 2 and 3 for a steady exhaust stream. This is a deeper reason why F equals mv works. Units used, kilograms, unit of mass, second, unit of time, ms, meter per second, unit of speed, velocity, how many meters something moves each second. Used for exhaust speed, VE equals 500 ms. kg/s, kilogram per second, unit of mass flow rate, how many kilograms of gas leave the engine each second. Used for m equals 10 kilograms per second. And Newton, unit of force or thrust. Constants involved, there's no universal constant needed like g. The values VE equals 5,000 ms and m equals 10 kilograms per second are given parameters, not universal constants. Reasonable variables, Newton and thrust force on the rocket, kgs mass flow rate of exhaust per second, ms exhaust speed related to rocket, kg mass of the rocket if used for A, ms2 acceleration of rocket if extended, kg times ms momentum of exhaust or rocket, kg ms change in momentum, s time alternative. Solution for the problem, step by step. Mass flow rate of exhaust, m equals 10 kilograms / s. Exhaust speed related to rocket, VE equals 500 ms. Step 1. Choose the correct formula. For a rocket, jet thrust is F equals m times VE, where the F is equal to thrust, m is equal to mass flow rate, and VE is equal to exhaust speed. Step 2. Substitute the numbers. F equals 10 kilograms per second times 500 meters per second. Step 3. Do the multiplication. 10 times 500 equals 50,000, so F is equal to 5,000. Step 4. Convert units to newtons. Remember, 1 N is equal to 1 kilogram, so F equals to 5,000 newtons. Final answer, 5,000 newtons. Verification for the problem. Checking the math. Problem recap. Mass flow rate of exhaust, M equals 10 kilograms per second. Exhaust speed, VE equals 500 ms. Find the thrust F. Formula for thrust, F equals m times VE. Plug in the values. So F is equal to 5,000 mathematically is correct. Checking if the value is reasonable. Check against expected size of the force. If the mass flow rate were 0 kilograms S, thrust should be 0. That fits the formula. If we double the mass flow rate to 20 kilograms per second, thrust would be F equals to 20 times 500 equals to 10,000 S. So 5,000 is right in the middle of a sensible range. For a small rocket or strong thruster, a few thousand newtons or thrust is very believable. So not something tiny like 5, nor absurdly large like 5 million N. So 5,000 is not too small. It would barely move a rocket. Not too insanely large like a giant heavy lift rocket. It fits the idea of a small test engine or a thruster. How the solution process is valuable to the project topic. It turns Newton's third law into numbers. Action. Engine pushes gas backward. Reaction. Gas pushes rocket forward. The calculation 5,000 N gives a numerical value to the reaction force, making the law real and measurable, not just a sentence. The process used to solve and verify it directly supports my project on modern jet propulsion in Newton.